Dear ladies and gentlemen, my name is Rico Ottermann from the Institute of Microproduction Technology from the Leibniz University of Hannover. I would like to welcome you to my presentation for the IEEE Census 2020 virtual conference with the title Direct Deposition of Thin Film Strain Gauges with a New Coating System for Elevated Temperatures. First of all, let me give you a short overview and the motivation of our work. Conventional strain gauges are polymer foil based as shown in Figure 1. At the Institute of Microproduction Technology, we work on a new approach, which is the direct deposition of sensors on components of arbitrary size with a new deposition system. The results are component-adherent sensors with thicknesses below 5 micrometers, higher temperature stability, and even higher measurement accuracy, which will be discussed within this presentation. The overall project goal is the process monitoring of bottom hole assemblies, as shown in Figure 2. If you look at Figure 3, you can see the cross-section of such a drilling tool. The usage of conventional polymer foil-based strain gauges requires milled pockets in the tool's surface. This is a weakening of the tool, which can be avoided by the usage of directly deposited sensors. Within this publication, the development of strain gauges on planar substrates is shown. The content of my presentation starts with the sensor manufacturing. Afterwards, I will show you the results of the characterization regarding the temperature coefficient of resistance, TCR, and the K-factor temperature dependency. Then, the temperature compensation capability of directly deposited half-bridge sensors is shown. In the end, I will give a conclusion and I will show you the outlook of our work. The sensor manufacturing takes place with a new coating system for direct deposition based on a sputtering process, as shown in Figure 4. It consists of a process chamber, which will be closed by the substrate itself for the vacuum process. That's the reason why it enables the deposition of components of arbitrary size. For our investigations, we chose stainless steel tensile specimens, as shown in Figure 5. The deposition starts with an alumina insulation layer, which is necessary due to the metallic substrate. Afterwards, the sensor layer is deposited. The structuring happens by the usage of silicon shadow masks, as shown in Figure 7. Different sensor materials are investigated in order to find the best material for our application. These materials are nickel chromium 8020, nickel chromium 6040, and constantan. The result is a directly deposited sensor as shown in Figure 8. The design consists of 2 half bridges with 6 contact pads each. This enables the 4-wire resistance measurement of the single strain gauges and the 5-wire technology measurement method for the half bridges. Now the pads are connected with conductive silver adhesive to a special circuit board which is designed for high temperatures. A PT100 temperature sensor is added in order to measure the temperature during the characterization process. The last step is an annealing step at 220 degrees Celsius for 10 hours in order to stabilize the resistance values. The characterization starts with a comparison of the different sensor materials regarding the TCR up to 200 degrees Celsius. The aim is to find the material with the lowest TCR amount to simplify the temperature compensation afterwards. The TCR is calculated by the resistance change, the initial resistance, and the temperature change. In Figure 10, the TCR values for single strain gauges R1 to R4 are shown. In the first 3 columns, we can see the results for the 3 sensor materials. The lowest TCR amount could be achieved for the constantan layer, even though the standard deviations were very high. In order to minimize these deviations, a protective layer out of alumina was added. The result is an average TCR of minus 51.5 parts per million per degree Celsius. With this evaluated layer stack, the K-factor measurement up to 200 degrees Celsius takes place in a tensile test stat. Therefore, the temperatures increase stepwise as it is shown in figure 11 with the green curve. On the left y-axis, we can see the resistance change of two strain gauges with the red and blue curve. At constant temperature values, for example at 60 degrees Celsius, 3 cycles of strain are applied. They lead to a significant resistance change, as we can see 5 times in the diagram. Out of these resistance changes, the K-factor can be calculated according to this formula, which is analog to the TCR formula, but now this time the strain appears instead of the temperature. The result is an average K-factor of 2.05, which is independent from the temperature. Next, the characterization is shown regarding the temperature compensation capability for half bridges. Therefore, varying temperature and load cycles are applied at the same time. The measured strain, according to this formula, consists of the K-factor, the Poisson's ratio, the input voltage and the output bridge voltage. The result is shown in table 1. The maximum error of 46 micrometer per meter is at least factor 5 lower than the value of commercial strain gauges, which are in a half bridge configuration. Even better values could be achieved by the usage of a second order temperature polynomial, which reduces the maximum error to only 10 micrometer per meter. The characterization procedure is shown in figure 12, where the temperature is increasing or decreasing all the time, and at the same time the strain cycles are applied, which would lead to a theoretical strain, which is shown by the red line. The blue line shows the measured half-bridge sensor signal with the second order temperature polynomial. As we can see, we have good accordance to the theoretical strain values with a maximum error of only 10 micrometer per meter. With these outstanding results, I would like to give you the conclusion and the outlook of our work. I have shown you the temperature behavior and the compensation capability of directly deposited strain gauges with a new coating system. Therefore, we used a layer stack consisting of constantin with an alumina insulation layer and an alumina protective layer on top of the sensor layer. The results for the single strain gauges were a TCR value of minus 51.5 parts per million per degree Celsius and a K-factor of 2.05, which was independent from the temperature. With the directly deposited half-bridge strain gauges, a temperature influence reduction by at least factor 5 was possible compared to foil-based half-bridges. As we can see, we were able to reach a higher measurement accuracy, which can improve the process monitoring in harsh environments such as there are underground at bottom hole drilling tools. Let me tell you about the upcoming work. At the moment, we're working on the technology adaptation for the coating of convex surfaces. If we look at figure 13, we can see our new approach. We use a curved shadow mask out of stainless steel, which is held by a shadow mask carrier. This system is pressed against the cylindrical steel substrate, which will be the bottom hole assembly later. The first result of a first sputtering process is illustrated in figure 14. Here you can only see the sensor structures in X direction. The reason for this is the fact that the sensor design has to be divided into 2 shadow masks for the X and Y direction. Otherwise, some parts of the metal shadow mask would not be in direct contact with the substrate because of its curvature. The alignment of 2 shadow masks to each other is quite important to generate the original sensor layout again. A comparison to the sensor results on the planar substrates will be interesting. Further research topics are the development of a wear protection layer, which has to protect the sensor structures from mechanical destruction, and the electrical feed-through of the sensor signals into the inner part of the drilling tool. Finally, I want to say thanks to the German Research Foundation, the DFG, that funded this work as part of the Collaborative Research Center 653 Gentilican Components in the Life Cycle within the Transfer Project T14. I would also like to say thanks to our project partner Baker Hughes and to the Institute of Microprojection Technology that I am allowed to work at this project. So now we reached the end of my presentation, and I want to say thank you for your attention and for listening. If you have any questions regarding my presentation or my paper, feel free to ask them.